Good morning, everyone. Thank you for making it. Today we have webinar number 18, episode number 18. My name is Alex Bassini. I'm the Business Development Manager and Water Treatment Specialist here at AWC, and we are joined by our own, very own Ryan Harvey, which is also on the Business Development team. Today we're going to be covering tube settlers. Something that's pretty unique on the tube settler front is just the technology has been around for so long. And as we progress, there's always new modifications and new changes and the ways of optimizing it. I apologize for the invitation that went out. I think some of them listed this as saying that it was in December. It's wrong. It is today. So thank you, everyone, for joining. As we let everybody join in, this is kind of the webinar series that we're going through. We're now at 18, so we're kind of adding a few more of those. We will be taking kind of a break in December as we kind of make plans for the holidays, but other than that, we do have about 25 or 26 that are ready. So a quick outline on AWC, if this is the first time that you're logging in. We've been around for 40 years now. We have well over 500 water treatment plants out there, both water and wastewater. The nice thing is that we do the design and the manufacturing front on them. So because of that, it's pretty nice to keep something compact, modular, and something that we can test before it ships. For those of you that aren't familiar with our plants, this is kind of what they look like. We divide them into three. We have both the potable water, wastewater, and of course our skid mounted systems. Tube settlers, which we're going through today, is more on the potable front for high turbidity and organics. I will let Ryan take all of that away, but you can potentially tie it in to some of wastewater applications if you're looking for a final polishing stage. I do want to point out that this week, and a shout out to our Brazilian friends that are going to be joining, AWC this week was part of the virtual water and wastewater trade mission in Brazil. And we've had some really good connections and meetings with them. So shout out to them if you've already logged in. This was administrative environment down there. And of course, if I have to throw this in, today is World Toilet Day. I know. We don't really think much when it comes to toilets. You just, flush and do your thing. But this is more of making sure that there is awareness around that, everybody needs toilets, everybody uses wastewater. It's easy to just flush and walk away. And quick slide, this is what toilets look like in some parts of the world. I know, very shanty. You will never look at your toilet the same again. And I've got a fun little fact in here before we get started. And I'm not picking on India because I know we have a couple people signing in from India as well, but in the last 3 years, the government in India installed 52 million community toilets. So picture this is 16 homes sharing 2 or 3 toilets. Unfortunately, there's no running water. So as you, obviously, if you've used a toilet before, toilet without running water is basically just a ceramic bowl. It doesn't do you much good. So now they're not being used. So anyways, just to raise awareness on the value and things that we take for granted. So with all of that, we're going to get into tube settlers. Ryan, I hope you're ready. Go ahead, take it away.
All right, I'm sharing my screen now. Alex, can you see it there?
I can.
Good. Good morning, everybody. Thanks for the introduction, Alex. As discussed, I'm going to be teaching you guys a little bit about tube settlers today. All right, so first of all, clarifiers are typically settling tanks that are used for the removal of solids through sedimentation. Clarification can also be done sometimes through flotation or adsorption, but today we're just going to be talking about the gravity type. Solids accumulate in the bottom of the tank and have to be removed periodically. And traditional clarifiers, like the one on the right here, is probably what most people picture when they think of a clarifier. It's got the big mechanical arm that spins around. These are massive circular tanks. They require an extremely long settling time and a huge footprint for sufficient removal of the solids. Today, what I'm talking about is lamella clarifiers. These have no mechanical moving parts. The two different types are have lamella plates and tubes. So tubes, of course, is what I'll be talking about. So on the left here, we've got a typical tube settler. We got coagulation and flocculation on the front end. This is a conventional water treatment plant. And then the water moves over into the clarifier section, which is with this middle section. it flows up through the tubes into the launder here and over into the filter on the backside. So basically, so the tubes are typically made of PVC, but they can also be polypropylene or FRP. They are angled at roughly 60 degrees, which is, I guess, has been determined as the optimal angle for proper settling. The tubes the tubes create a much larger surface area for the particles to settle on. They also reduce the settling distance, because if you picture the traditional clarifier I showed previously, some of those particles are going to have to settle from the very top of the tank all the way to the bottom of the tank. But in this case, the particles only have to settle the distance within each individual tube before they reach the bottom and start building up with other particles. So I guess the tubes also they help create laminar flow. So instead of having a bunch of swirling water around within the clarifier, they're forced up through these tubes, which allows for that laminar flow, which creates the best atmosphere for the particles to settle. So all of this, in summary, increases the settling rate of the particles, which fall to the bottom of the tubes, where they can aggregate and bind together and build into larger flocks, which then slide down the bottom of the tubes and then ultimately fall to the very bottom of the tank, where they collect as sludge. So here's just a cross section of a tube here, so you can kind of see the water is, of course, flowing upwards, and there are lots of calculations to see what the settling rates are, but as long as the tubes are long enough, by the top, pretty much all of the particles will have settled out if the design is done correctly. Just another image over here. So there is quite a bit of space between the tubes. Of course, the water's got to flow under before it flows up through the tubes, and then there's also got to be distance there for the particles to fall down and collect as sludge. So, like I said, all of this allows for an increased loading rate through the clarifier. It reduces the amount of retention time required, and it creates you can push about 2 to 4 times the flow through one of these clarifiers as compared to a traditional clarifier. So tube settler advantages: they can handle extremely high turbidity, from rain events and whatnot. By increasing the settling capacity, the tube settlers also increase the flow capacity per unit of area, as I mentioned. So this translates to a rate of operation 2 to 4 times the normal rate of a conventional clarifier, which means that new installations can be made significantly smaller because of the increased flow capacity. The tubes are lightweight and low cost relative to lamella plates, which have similar performance advantages. The tube settler clarifiers have no mechanical moving parts to maintain, and they can also be retrofitted into any existing tank. So if somebody wants to gain extra capacity out of an existing tank or clarifier, they can use tubes, a tube pack, and install that into that tank in order to increase the capacity. Rough sizing, sizing is very dependent on the water quality, and so higher turbidity waters and especially cold water, especially right around 4 degrees is where water is most dense. It has the tendency to carry smaller particles a lot easier. So sizing is definitely dependent on your raw water quality. However, for a rough rule of thumb, we typically try to keep our clarifier section down to less than 1 GPM per foot squared. And that's kind of for optimal treatment. With lower turbidities and waters that don't see large turbidity spikes, of course we can increase this rate a bit. So yeah, for estimating a rough footprint, we typically we assume that on the higher end, these tanks can we need to ship these tanks, so they can be roughly 12 to 14 feet wide at a maximum. So taking this 1 GPM per foot squared, you can calculate what length you might be looking at in that scenario quite easily. Applications and limitations, very regularly used on potable water. We typically use them as a go-to for high turbidity applications. We've used them on applications up to 2000 NTU and above. They're also quite good at removing organics from water as well, from surface waters. Another scenario they can be used is secondary clarification of wastewater. Limitations, like I mentioned, that cold water carryover, small particles do have a lot more trouble settling in that cold water. So we do typically need to slow down the flow rate in preparation for that. Additionally, the tubes do need to be cleaned regularly. Typically, it's about every 6 months. The tank needs to be drained and the tubes need to be sprayed down. I just put in this image on the right. We do have lots of tube settlers out there treating water that does look like this chocolate milk river here. And the communities are always, they're absolutely astonished when they see the crystal clear water coming out the backside of our plants. It's amazing how much turbidity these plants can remove. So when it comes to optimizing the design, the two main factors are sludge management and ensuring that the velocities through the tubes are uniform. So when it comes to sludge management, it's important to properly maintain the sludge blanket height, and uniformity of height, I guess, is more critical. And the reason for this is that ideally your raw water will actually pass through the sludge blanket as it enters the clarifier, which allows for preliminary filtering of the raw water, and especially helps remove those smaller particles. Additionally, and this is a bigger problem with flat bottom tanks, is sludge dead zones. So if there are spots where sludge isn't being properly collected over time, that sludge can turn anaerobic, which allows for the growth of harmful bacteria and the creation of gases, which definitely affects the quality of treated water. So definitely not a good scenario for potable water. Like I said, also the second factor is uniform velocities through the tube. So if your clarifier has a whole bunch of eddies and inconsistent flow velocities, we call it maldistribution of flow. You're not going to have consistent treatment of the water, because some of those solids will be passing through some tubes, and some of the tubes with lower flow rates will have those solids settling. So it's much better to ensure that there will be uniform flow through the tubes. Additionally, if there isn't uniform flow, there's a good indication that there is short circuiting. So if you've got a designed retention time in the clarifier, and you have some of that water circuiting, which means it's basically just passing right through and not spending the amount of time it's expected to spend in that clarifier, that's a huge disadvantage, or a huge design flaw. Additionally, eddies in the flow can carry solids that stir up the sludge blanket, and it can minimize the ability to achieve laminar flow within the tubes. So this is I don't know who manufactures this design here, but this is an example of a design where, as you can see, we come in, we coagulate, and we flocculate here, and then as the flow passes into the clarifier section, it just kind of shoots out this one side, which is going to create all sorts of eddies and just general maldistribution of flow all over this tank, and it's got the potential to stir up the sludge. Additionally, if a manufacturer in this case wants to increase their flow capacity, they'll typically just increase the length of this tank. But as you can see, if the flow is just coming in here and they increase the length, it's more likely that this water is going to simply just short circuit, pass right up through these tubes, and go out through your filter, which is going to have you backwashing this filter all the time, far more often than necessary, and you're going to have kind of dead zones where the water isn't passing through nearly as much as it should be. Again, like I mentioned, the flat bottom tank is an issue for sludge removal, and creates a pretty significant possibility of those dead zones that can turn anaerobic. This is another design, quite one. This one potentially has a little bit better ability to create a consistent flow velocity through these tubes, but at the same time, as you can see, we're still flowing down and around. there's possibility for some eddies here. Definitely possibility to bring up some of these solids. And again, we've got the flat bottom here. So for optimizing the design, it's best to have a distribution manifold that reaches the full length of the clarifier and allows for the same flow velocity out of the nozzles at the end as it does at the start, so that you have a perfectly uniform upward flow through this tube pack. Additionally, a V-shaped bottom, and I'll show you a little bit better on the next slide here, but a V-shaped bottom allows for the sludge to be collected much more evenly and allows for better control of the sludge blanket height. Like I said, we want that flow to actually pass through the sludge blanket on its way into the clarifier. So as you can see here, it's just another few angles of this. These are the distribution manifolds I'm talking about. You know, they reach the full length, and same with the sludge collection channel at the bottom here. It also reaches the full length. So that just allows us to control the flow upwards, as well as the sludge blanket height can be maintained at a perfectly uniform height. So this flow actually passes through the sludge blanket as it passes up. The result of that is a tank where you can barely even tell it's running. This tube settler is in operation. You can see the water flowing into the channel here, but because the flow through these tubes is so uniform, it's crystal. It's like it's clear as glass on top. Lastly, you may think that this luscious lip sweater that I'm sporting right now is my standard look, but unfortunately for my wife, I will be shaving this at the end of the month. I'm growing this for Movember. There's a team of us at AWC that are doing this. You know, if you read the stats that Movember is trying to improve, it's a pretty important movement, and I urge you to consider donating. So I believe Alex will send out the link to our team page when he sends out the YouTube link, so you can consider donating at that time. Thanks, everybody.
Thank you, Ryan. That was great. Oh, looks like there's an echo there.
I don't hear the echo, Alex.
No, you're good? Okay. Excellent. So I don't know if you can, we're kind of opening it up here to some questions and answers. I don't know if you can all see this slide that it has, kind of with a little announcement of what we're going to be doing next. But there is a chat box. Everybody's familiar with that. It's on the top right-hand side if you want to punch anything in there. Don't be shy. If you want to turn on your camera, by all means do. I do have a couple questions. I was taking some notes here. So if you don't mind, I guess my first question is, you had mentioned that there was some media. You were using anthracite as a fall at the very end of a tube settler.
Yes.
Are there specific media considerations that you should be using at the polishing stage?
Yeah, so typically we'll do anthracite, Alex, above a layer of sand, and in some cases, you know, clients will request also there to be some gravel down at the very bottom. But yeah, we can use different media for different contaminant removal. You know, green sand is a common one, so often we'll have anthracite above green sand to enhance manganese and iron removal.
Okay,
so
and
that can be varied depending on the contaminants we're targeting.
Of course. And you had also mentioned cleaning. Are there specific steps or instructions, or do you use any kind of chemicals in order to clean it? Or is it just a simple shut the unit down, do some backwashing on it?
Typically, it's just you know, shut the unit down, drain it. You need to spray down the tubes. Be very careful to get, you know, inside of each individual tube there to clear out any sort of sludge that's collected. Oftentimes, operators will go too long in between cleanings, in which case sometimes you know, some chemicals may be required, but typically just the pressure of a spray down is enough to remove any solids that are in those tubes.
Okay. All right, here we go. We have a question coming in. All right, here's another one. So as far as you said that there was a laminar flow going across. So when you see it very steady, you know, just glass going through it, you know that it's working regardless of flow. If there's any ripples or there's any movements, what would cause that, rather? Is there a troubleshooting way of understanding where it's coming from?
That's a good question. It's tough to tell what's going on inside the tank without taking a better look at the inlet to the clarifier section. But it is a good indication that you have some eddies or some uneven flows within the clarifier, to potentially rectify that, baffles or something else to kind of slow down that flow as it comes into the tank there.
Excellent. Okay, well, thank you for that. Thank you, Ryan, for joining us today. And yes, I can't grow a mustache to save my life, so I will leave you to it and the rest of the AWC team. I think you're doing a great job, and I'm sure they will be very happy once you take it off. It looks like we have another question coming in. Give me a second. All right, we have a question from Sonia. Oh, hi, Sonia. So Sonia's logging in here from Brazil, part of the trade commission that we did there. Trade mission, excuse me, the virtual trade mission that we did with the Canadian Trade Commission. So her question here is, the cone has any kind of scraper, or does just flushing it with sludge pump enough?
Hi, Sonia. Yeah, I assume you're talking about the cone at the bottom, like the cone, if you have a cone or a V-shaped bottom. No, it does not have any kind of scraper. Removing sludge with the sludge pump is sufficient. However, when you do clean those tubes, it's best to spray down the whole tank as well at the same time. And I see your other question there is, how often does the sludge need to be removed from the settler? That's something that's kind of fine-tuned over time. So, you might be removing sludge every few days, or sometimes, depending on, heavier loaded water may require it, once a day or more. So that's kind of a process that gets automated over time, but it does require monitoring of the sludge accumulation over the first few weeks of operation in order to nail that timeline down.
All right, that's great. All right, well, thanks again, Ryan. We are now hitting the 23-minute mark, and we try to keep things on time, short and sweet. Thanks everybody again for joining. Next week we're going to be touching on trihalomethanes. We're going to be going over some chlorine and chloramine and how they interact with water and some disinfection byproducts. Of course, we're also going to have the YouTube channel where this is going to be listed. You'll be getting an email tomorrow with a link if you want to follow up. If anybody wants to stick around and has any follow-up questions, if not, thank you very much for coming, and goodbye. See you next week.